So in this clip, we're going to look at the example of this transformation here. R of uv is given by u plus v over 2 in the first coordinate and u minus v over 2 in the second coordinate. And we'll see how this can be used to set up an integral. But first, let's understand, well, the reason why this clip I called it linear is just because the coordinate functions that I'm using, the change of variables, is these are linear functions of u and v. And what I mean by that is that u and v appear as variables to the first order, but not to the second or third order. There's no quadratics or cubics, Freudian slip. And u and v are not multiplied against each other. All it is just number times u plus a number times v, that's it. So this is very simple. Now, linear transformations can only do a certain limited number of things to a given plane region. They can scale it, rotate it, reflect it. They can shear it, meaning it might be the case that the image of this square I've drawn here comes out looking like a parallelogram afterwards. And then they can also project, so something can get flattened. But that's not going to be the case here because that wouldn't be very good for working out coordinates. So let's see what this does to our region. So first of all, let's investigate this square here just a little bit. So the red line, that's where u is equal to 0, and the orange one is where u is equal to 1, and the green is where v is equal to 0, and the purple is where v is equal to 1. Okay, and so let's look at the image of these various curves under the transformation. And so let's see, let's start with the green one here. So if I look at the green one, this is where v is equal to 0. So then my coordinates are, let's see, I've got x equals 1/2 u and y equals 1/2 u. Oh, so this is where x is equal to y, and as we go from 0 to 1, we get to the point 1/2. So, which is, oh, well, that was a little bit sort of slanted. Let's see. There we go. Okay, so here's the point 1/2, 1/2. All right, so that's what the image of the green one looks like. Now, what about the yellow one? So for this one here, now we're looking where u is fixed equal to 1. So x is going to be 1/2, and then we've got 1/2 v, and y is going to be 1/2 minus 1/2 v. So the y coordinate is going to decrease. So in other words, we're going to be going downward as v increases, but the x is still going to increase. So we'll be going that direction. And so we come down to this point somewhere here. Okay, and now if we look at the purple one, the purple is where we've got v is equal to 1, and then u is going to be decreasing. So let's see, so we've got x is going to be 1/2 u plus 1/2, and then this is u is going to go from 1 down to 0. And that's not any kind of real notation, that's just sort of a little note to myself. I could just as easily have done, whee, flippy arrow. Y is going to be 1/2 u minus 1/2. Okay, so, okay, so we're going to come down to here. Work with me. All right. And then you can see that the last part is going to come back up to here. Okay, so this is how we're able to figure out what the image of something looks like under a coordinate transformation. So it looks like a square that's been rotated by 45 degrees and then flipped. You'll notice there's an orientation change. If we started by going green, orange, purple, red, and it was counterclockwise, then green, orange, purple, red is now clockwise afterwards. So there is an orientation change. And so let's see. So, and we also see that we ended up with a smaller region. And so this is all reflected in the computation of the Jacobian, because the Jacobian is supposed to keep track of the area or volume change while doing a parameterization, right? So it's our chain rule. So let's see. So we've got top rows for x, bottom rows for y. By the way, there's a couple places in the book where they actually have these guys swapped. That's an error. It's supposed to be like this, where your x's go across the top and your y's go across the bottom. Each function gets its own row. Okay, so this is, let's see, so if I'm taking partial derivative of x with respect to u, I get 1/2, and with respect to v, I also get 1/2, and y with respect to u gives me 1/2, and with respect to v gives me minus 1/2. And so then I do this product minus this product, and so I have minus 1/4, and then I subtract a positive 1/4, and I end up with minus 1/2. And if you check just visually, you can confirm that this right here is one of these sections. Oh, sorry, I drew the wrong one. This one right here. So that in fact, this guy is exactly half the area of this guy. And that minus sign right here, that's exactly the orientation change that I was talking about before. So it all adds up.